This is part 4 of our lecture for the third week in physics. We're going to finish up talking about the addition of velocities in terms of x and y vectors. We've been talking about this all along, but I'm going to show you in these last few slides how we can use this on motion other than projectile motion. As we've seen before, the velocity of an object traveling at any particular angle can be divided into a horizontal and a vertical component, and the sum of these two components make up the vector that represents the velocity vector. Now here's an example of what I'm talking about, not applied necessarily to projectile motion. Here's a boat that's trying to go from the bottom of the slide to the top of the slide. These are the two banks of the river, and it's trying to row straight across the river, but it's going with a current, and this current is moving from left to right in the x-axis. And so the boat itself, because of the effect of the current and the effect of the rower, will have a motion that is more accurately depicted by the line, which is measured v total. This is what is seen relative to the shore, and it represents the sum of the velocity of the rower and the velocity of the current in the river. Here's another example, and in this example what we have is a plane that's trying to travel straight from the bottom of the page to the top of the page, or you can say is trying to travel due north. However, this plane also has a wind in its face that's traveling from east to west and modestly south of west, and it's shown with the VW. So here's the vector representing the velocity of the wind, and here's a vector representing the velocity of the plane. Now the impact of these two vectors is what we see in the actual velocity of the plane, which would tend to slow the plane down but also blow it westward off course. So how do we take this into account if we put actual numbers in this situation? Okay, according to the problem, the airplane is known to be heading north at a velocity of 45 meters per second. So the plane's velocity, represented by Vp, is 45 meters per second due north. And at the same time, the actual ground velocity is shown at 38 meters per second. And this 38 meters per second is at an angle of 20 degrees west of north. So the question is, what is the speed and direction of this vector right here, the wind vector? So this is another situation where you can divide these into a x-axis and a y-axis. This is due north, so this only has a y component, so it's going to be simple. It's 45 meters per second, right? The v total is going to be equal to v total x and v total y. So it's those two vectors together. And v total x is again calculated in the same way we've calculated this in the past. The x component, as you can see over here, here's the v total. So the x component is here, which is the side opposite the angle that we're talking about, So it's going to be V total times the sine of 20 degrees, and V total y, and it's going to be this part, and so that's the side adjacent to the angle, so it's going to be V total times the cosine of 20 degrees. So this is going to equal 38 times the sine of 20, and this is going to be 38 times the sine, or excuse me, times the cosine of 20. So let's do the calculation. So 38 times the sine of 20 is 14 meters per second, and 38 times the cosine of 20 is 35.7 meters per second. Now the wind, the y component of the wind is the same as the y component of, the x component of the wind is the same as the x component of the total. So the x component of the wind is going to be this number right here. The y component of the wind is going to be equal to 45 minus the y component 38.7. So the y component of the wind, which is shown as P, is going to be 45 minus the y component of the total, which is 35.7. So that's going to equal 9.3. So the wind is equal to the square root of 35.7. Nope, not 35.7. I'm sorry, that's incorrect. Let me erase that. It's going to equal 14 squared plus 9.3 squared. It's actually a minus 9.3, but we'll use 9.3 since it's squared. It doesn't really matter. And if we do the math here, so the total here is 16.8 meters per second. And then if we look, we can use this 16.8 meters per second. We know that's the hypotenuse, and we can do several different calculations. We can use the 9.8 or 9.3 divided by 14, and that's going to be equal to the tangent of the angle we're interested in. And so the angle is going to be the arctangent of that. And you're going to have to look that up on your calculator, because my calculator doesn't do inverse tangent functions, so I'm not going to be able to do that for you. But if you put this number and find the inverse tangent of that, it'll give you the angle. Okay, let's look at another example. Here's the boat we were talking about, and I'm going to let you work on this. But notice that we have a boat that's being rowed at 0.75 meters per second, and the current of the river is 1.2 meters per second. And what we want to know is what is the actual V total, or the velocity that we're looking at. And then you can also take a look at the displacement relative to the shore. That is the length of this side relative to the shore. However, you would have to know how wide the river is or how long you rowed in order to show the actual displacement. What I think they want here, this is not a very good term for it, what they want is what is this velocity vector for the actual boat velocity. And I'll let you work on that, and if you have problems with that, you can bring it to class on Monday. Now here's my last slide, and I wanted to use this as something that we can work on to finish up our work. And what this says is you have a ice hockey player who's moving at 8 meters per second, and he's moving 8 meters per second, we'll call it due north, and he hits the puck toward the goal, and the speed of the puck relative to the player is this way at 29 meters per second. The line between the center of the goal and the player makes a 90-degree angle to his pass. So what that means is he's going due this way, whereas the angle is this way. What angle must the puck's velocity make relative to the player to hit the center of the goal? So the question is, what is this angle right here? So this is how we would do it. You see that, again, these are two parallel lines that are being intersected by a single line right here. Now what we said was that these two angles, or this angle here and this angle, they're going to be equal. So this angle, theta, and this angle are equal. So this is the side opposite. So v puck, the velocity of puck, times the sine of this angle is equal to the velocity of the player. So the velocity of the player is equal to the velocity of the puck times the sine of theta. Okay, so that means that the sine of theta is equal to the velocity of the player divided by the velocity of the puck. And that means that theta is going to equal the sine minus 1, or the inverse sine function of this, and we know the velocity of the player is 8, and the velocity of the puck is 29. And so if we do the math here, we get 16.01. So this angle and this angle are both 16.01, but the question is, what angle must the puck's velocity make relative to the player? So it's asking what this angle is. Well, we know that this angle plus this angle is 90 degrees, so if we subtract this from 90, we'll just get rid of that, it's 74 degrees. So the answer is 74 degrees relative to the player.